I'll start sharing my screen. Hope my screen is visible. Is my screen is visible? Hello?
Yes, ma'am.
Okay. Let's wait for 2-3 minutes more. Then we'll start the class. Recall all those notes you have with you. Last class we found out nominal stress, or you can call engineering stress. Then we found out engineering strain, right? 21.
Ma'am,
Yes, yes.
ma'am, I didn't find any notes on loading and all those second or third lecture classes in our ERP.
You didn't find any notes. Okay. Okay, I'll share the PPT in the group. I have shared the PPT till lecture 3, right? In
Uh,
in
uh,
in our
yes,
group,
ma'am.
I have shared the lecture till 3, right? Today I'll share 3 more lecture
Let me-
4, 5 and 6. Okay, today will be lecture 6. So I'll share all the 3 lectures today in the group. Okay, let's start. My screen is visible, right? Hello? My screen is visible?
Yes, ma'am.
Okay,
Yes, ma'am.
okay. Let's start. So today we'll discuss stress strain diagrams. What is stress strain diagram? Then we'll see the material properties associated with stress strain diagrams, Hooke's law. Then we'll discuss material property associated with, we'll continue with the same topic, and then we'll identify 0.2% offset yield stress. Okay, as the subject defined mechanics of material. So you should know how the every material behaves. You should know the basic properties, right? So for that, just a little bit of review. We have considered a member. We stretch it out. We have applied a load in axial direction. Then that member has stretched out. Let me note. We have considered a member, right? My cursor is moving. My cursor is moving. Hello, please.
Ma'am? Oh, yeah.
My cursor is moving, right?
Yeah.
Okay. So last class we have considered a structural member, right? We have applied a axial stress on the member. Then this member got elongated, and we got a elongation as delta. Then we did a transverse cut on this member, and we found that normal this P will be equal to this normal stress. Then we studied the normal stress, which is force per unit area perpendicular to the cut surface. In that normal surface, we have two type of stress, nominal stress and true stress. In nominal stress, we take force per original area, and in true stress, force per area which we got after the deformation. In the same way, we studied the strain part, which is elongation per unit length. In this also, there will be two strain, nominal strain and one true strain. Elongation per unit original length. Let's move to the next part. So tension test. When we study for the material behavior, we generally do tension test. Let me note once again. So we did a review, then we apply, then we did a okay. That was the review part. Okay. Now let's move to tension test. To examine material properties, any material properties, we can perform tension test. Why we do a tension test? In graphing the results, we will plot stress strain instead of force and change in length. We got stress in terms of force, and change in length, right? But in graphing it will be easy if we plot stress and strain for material behavior. So to examine material properties, we generally perform tension test. You can Google what is tension test, and you can get a lots of video over the internet. So go with note down, just go through the tension test. So in graphing the results, we'll plot stress strain instead of force and change in length. This allows for the removal of geometry from the problem and allows the results to be used for different geometrical shapes of the same material. We'll look at this diagram in more detail. So see, this is the linear part. This is, suppose I'm taking a spring. Okay, I cannot show you practically, but surely I'll share a video. Suppose this is spring. Okay, this is a hard spring. If you stretch once, it will gain into its original form. That is this part. Whatever you applied stress, it will till here. Your this spring will it's come back to its original position. So this is called a linear elastic region where stress and strain are directly proportional. You know, na? This is the graph when this stress and whatever be the stress, it will give a strain and it will reverse back to its original shape. When you apply a load more than this stress, then it will start elongated and it will at some point it gets fractured. Suppose this is a rubber band. You will stretch it, right? It will reform into its, or suppose this is a rubber band. I'm assuming this is a rubber band. If you stretch it for some time, it will it will regain its original shape, whatever it is. So this is that part. Every material, if you applied a load in permissible limit, it will remain in this part. Means stress will be your directly equals to the strain. Whatever you applied the strain, the strain will be same. Okay. But after some time, when you stretch it more again daily, if you stretch it, yeah, if you applied a load which is not permissible by this band, then it will elongated.
Elongated.
It will elongated like this.
Elongated like
This is your nothing but
this is nothing but
it, my voice is.
my was.
Hello.
Hello?
Are you able to see this?
Are you able to see this?
Why?
Yes, ma'am,
Yes,
but
ma'am.
your voice is
But your
echoing.
voice is echoing.
Hello. Now?
Hello?
Okay.
Now?
Again. Hello.
Hello?
Again. Let me switch off my microphone.
Let me switch off my microphone.
Just wait a minute.
Just wait a minute.
I'm sharing my screen. Let me know if it is visible or not. Are you able to see my screen now? Screen is visible? Response?
No, ma'am.
No. Just wait for a minute.
Tension comes in the
Now? It is visible?
tension test.
Yes, yes, yes.
Ma'am.
Tension test. Yes. Okay.
Seema, Kumari. Stress.
Tension test. I'm showing tension test. So what when we start with the
Yes, ma'am.
okay. Okay, to examine material properties, we can perform tension test, and in graphing, the results will plot stress strain instead of force and change in length. In stress and strain properties, we found out for force and change in length, but to know the graphically about all the material properties, we generally put stress and strain. So, okay, in graphing the results will plot stress strain instead of force and change in length. This allows for the removal of geometry from the problem and allows the results to be used for different geometrical shapes of the material. Okay, for different material behavior, there will be different stress and strain graph. You can Google it for the steel, for elastic rubber, for different material. There will be different stress and strain graph. This is a general graph which will tell you the material behavior of that material. This graph, if for rubber, this will be graph another shape like this. It will have some same part, linear elastic part, then it will go to non-linear elastic part, and it at some point it gets fractured. So different material has different stress strain graph. Okay, so this generally allows for the removal of geometry from the problem and allows the results to be used for different geometrical shapes of the same material. Okay, this is the linear elastic part where stress and strain are directly proportional to each other, and then material starts to yield to fracture until it starts yielding until it fractures. Okay, so generally when as the load is increased, as the load increases, material used to get fractured from its it gets deformed. Suppose I'm considering a spring. Okay, if I stretch, suppose it can take a load of 50 kilonewtons. Okay, if I stretch, it can suppose this spring can take a 50 kilonewton load. Suppose I am stretching this spring by 35 kilonewtons. Okay, I am giving it a load of 35 kilonewtons. So this spring, it gets stretched, and after some time it will reform to its original position. So this part is generally this part, linear area, where your uh, where your structure whatever we give the stress, we give the stress, we'll get the strain. Okay, whatever we get the stress, it will be same. Okay, whatever we give stress, we'll get the same strain. So this part is linear elastic. This part is generally called as linear elastic part. So as a specimen is continuously loaded, you will notice that it starts to neck down, okay, or becomes smaller in diameter until it finally fractures. Okay, this is a typical tension test of a material. This will be stress, which is nothing but F by A, and stress is your elongation per unit length. And as I told you, different diagrams for different materials. You can search over internet stress strain diagram on the internet. Okay, stop annotating. We'll move to the. I the only one seeing a small window. Either am I the only one seeing a small window on the screen? Small window.
Ma'am,
Yeah.
ma'am,
Yes, yes.
uh, yes, something's covering over this tension test, like about outcome meetings and all. I
Are
cannot view properly.
are you able to see the okay, you have are you able to see the tension test and the stress strain graph
Yes, ma'am. Yes, ma'am. But on the right side, it's covering.
on the right side? Maybe it's covering your now? Now?
Maybe, ma'am, it's about reminder about upcoming meeting. It's still now, ma'am. Upcoming
What about
meeting.
others? What about others? They're able to see the whole screen? Give me a screenshot in the group.
Yeah, ma'am, same case.
Give me a screenshot in this group. Someone please give me a screenshot in the group. Then I'll able to know what problem you are facing. What is the issue with my screen? Give me a screenshot. Let me share it once again. Oh, due to network, screen has got shut down. Let me share once again. Now it is visible. Whole screen. Whole screen is visible now. Yes or no? Okay. Others? Screen is visible. Whole screen is visible. Okay. Okay. So let me explain you once more this graph. So as I told you, let me change another color. As I told you, this is a stress strain diagram. So to know the material behavior, how this particular material will behave, we generally do stress strain diagram instead of force and elongation. Okay, we generally do stress strain diagram. Different material will have its different stress strain diagram. You can Google it in your in internet. So whatever be the material, always it will come back to its original position when you apply a load at certain limit. Suppose this is the limit. After this point, it will start yielding, and it will yield, and some point it gets fractured. So this part is called as linear part, and this is your non-linear part. Okay. My cursor is moving, right? My cursor is moving, right? You able to see how it is moving and how I am explaining? Type yes. Anyone? See my network. I have very network.
Sometimes it's moving. Yeah.
Okay, it's not synchronizing with.
Sometimes it's moving. Sometimes it's not moving.
Okay.
Yeah.
Okay. Right now, adjust with this. I'll make a video. Otherwise, it won't be possible to take online classes like this. Okay. So this is the yielding part, this is the linear part, and this is the non-linear part. So at this point, material will be comes to its original shape, and from this part, material will start yielding, and it will fracture at some point. Okay. So this is the stress strain curve. You will get different curve for different members. So let's draw a stress strain curve. Suppose Here I am considering a stress. Here I am considering a strain. So at first you will have linear part, then it will around like this. See, this is the basically your stress strain curve. The material will first behave as linear. So at this till here, whatever you give the stress, it will come back to its original position. So this part is called linear region, and upon this stress is called is a proportional limit. After some time, it will deform a bit, but so up to here, up to this point, this region is called elastic region, and this point corresponding to stress is called is a yield stress. Again, if we applied more stress, it will elongate till some time. This is very long stage, and this is called perfectly plastic yielding. This region from here to here, this region is called perfectly plastic yielding. After this point,
Ma'am,
yes, yes.
ma'am, we can't hear you. Your voice is cracking. It's not clear at all.
Network is not good. Can't hear anything. Okay, let me do one thing. Write all of you write your attendance in the chat box. I'll do one thing. Just shortly, I'll make a video, and in the next class, I'll post the video in the class itself. Is it okay? I'll just make a video of this class, self video. Then I'll post in Cisco Webex. In the next class, I'll just play the video. You just stop me where you don't understand. Okay? Write your roll number in the chat box. So join the next class. Don't leave the class now. Okay, I'm marking the attendance. What I'll do, I'll make a video and I'll close the video in the next class. So that it will be easy, I guess, for you. And those who join, please join with your name and roll number along with that. Just like Gyani Jamatia 014 in the way. Name and your roll number. Not the whole roll number, just the number will be sufficient. And it becomes easy for me to track down. All of you wrote their roll number? Okay, you can leave the meeting. I'm ending the meeting.